All right, so I'm kind of reviewing quickly back through 2.3, which I had put up videos for. It was all about set operations. And which means ways to obtain a new set, generally through what we would call binary operations. That is taking two sets and combining them and obtaining a third new set by some rule of operation. Now, technically, we had looked at one operation prior in 2.2, and that was complement. So I'm just going to list out all the operations here. So we'll consider complement, set complement as our first operation, but it's really an operation onto just one set. And we denote it with a prime mark, and we say, and we see that a complement. And what that basically is, it's everything in the universal set except what's in A itself. So that is X such that X is an element of the universal set, and X is not an element of the set A. All right, so complement of a set. Now the set operations that are, these are all binary that were discussed in 2.3. First one we're going to look at is intersection. Now it's denoted with a capital upside down U. So if we have two sets A and B, this is read A intersect B, and it is the set of elements that are common to both A and B. So to be in the intersection, you have to be in both A and B. So we'll say X such that X is an element of A, and that is the key word, and X is an element of B. So over here we'll put complement. And this is intersection. And the third one will be what we call union, and it's denoted with a capital U. And in this one, to be in the set, it's a little less restrictive. You either have to be in A, and the key word here is or. So you can be in both, but you have to at least be in one or the other. And so I always think of it as take the two sets and dump them in a big hat, and you've got the union of the two sets. The fourth one is called set difference, and it's denoted, looks like a subtraction symbol, and it is read A not B. So to be in the set difference, all the elements, and it's just how we read left to right, all the elements have to be in A. It's just a matter of, do I remove anything? And the ones I would remove, so it would be X such that X is an A, one on the left. But anything that is in that B we'll take out. So if A and B are disjoint, that is, they have nothing in common, then A not B would be A. There wouldn't be anything to take out. And again, this is referred to as set difference. All right. Now, these four I can represent with what we call a Venn diagram, V-E-N-N. Named for a guy named John Venn, who came up with the idea. So I'm going to draw a Venn diagram, small for each case. And here, set complement, if I'm going to represent a complement, I'll draw one circle representing A. And we shade what would be representative of the elements in the set. So we're saying everything outside of A. So I would shade everything outside that set A. That would be the Venn diagram representing a complement. Intersection of two sets. It's Venn diagram. Draw the box. Here. So we've got two sets we're representing. So I interlock them. And so here's set A, here's set B. And I would shade what, since it is the set of elements common to both A and B, I shade that part where they overlap. Union, so there's universal set, sets A and B. In this case, since you have to either be an A, be in the union, or B, minimally, but you would also include the elements that are in both. So at least in A or B. So basically you shade everything in A or B. And the last one, the set difference. Two circles, A, B. In this case, if it's A not B, then I want everything that is in A except throw anything out that's in B. So I would shade just the portion that is in only A. And that would be A not B. It's Venn diagram. All right, there was one more set operation that can't be represented with a Venn diagram. And it's officially referred to as Cartesian cross product. And Cartesian is just a derivation of a guy's last name, Rene Descartes. And it looks, so I hear product, so I think multiplication, and I use multiplication symbol to represent it. Now, this is red, A cross B. Now, the reason I can't draw a Venn diagram to represent this is the nature of the elements. An element in a cross product is an ordered pair. So that is a pair of numbers in an order. So every element of a cross product is an ordered pair. So I'm going to say ordered. So ordered pair AB such that, so how I find those ordered pair is, order again here is important. So such that the first component comes from the set on the left. And the second component comes from the set on the right. All right. And again, this is referred to as Cartesian cross product. So we're going to shorten that down and just say cross product. Those two sets A and B. So since the order is important, this is not what I would call a commutative operation. Addition is commutative. I can, regular old addition, I can add two numbers, different orders. 2 plus 3 is the same as 3 plus 2. Multiplication, which is repeated addition, is commutative operation. 2 times 3 is the same as 3 times 2. But if I find the cross product of two sets A cross B, that will not be equal to B cross A. All those ordered pairs would end up having their components transposed, and an ordered pairs only equal if their components are equal. So not a commutative operation. So i.e. Not commutative. A cross B is not the same thing as B cross A. But what is the same, and this is kind of where the multiplication idea comes in, is their cardinality. Turns out that the cardinality of A cross B is the same as the cardinality of B cross A. And you can find the number of ordered pairs simply by multiplying the cardinalities of the individual sets. So that if you had cardinality of A to be 8, and cardinality of set B to be 7, you would know that the cardinality of the cross product, either A cross B or B cross A, that there would be 56 ordered pairs, because it would have to be 8 times 7. And again, that is a quick review over the set operations in section 2.3. Though, again, I'm going to still give you the link to the entire lecture with examples from myself, in addition to the videos that I had posted last Thursday. Any questions? All right. So today, we'll look at section 2.4, in which we're going to look at coming up with in both kind of application problems and in more and others, and more of a kind of just mathematical, coming up with an exact number that would belong to a region using Venn diagrams. So this section primarily is about using Venn diagrams to solve what we'll call survey problems. Now you're going to have a few problems dealing with what we call cardinal number formula, which was technically introduced in 2.3 within the homework, but isn't officially really introduced until 2.4. In that video lecture link from yesterday, I will send, I do talk about this at the end. I'm going to review over it right now. So cardinal number formula. So cardinality, which again, remember, that's just the number of elements within the set of A union B. Now, it would seem reasonable that the number of elements in the union of two sets would be simply take the cardinalities of each set individually and add them up. And this would be true if A and B didn't have anything in common. That is, that they were disjoint sets or their intersection is empty. The problem will be if there is a common, at least one common element between A and B, this equation won't balance. This one will always end up being more. And what's happening is, because remember, if you take a union and you dump all those elements together, you don't write if they have a common element, you don't write it multiple times, you just write it once. So what ends up happening is this here will always be more because I'm counting elements twice on that side. So this is we'll just say only true if A intersect B is the empty set. They have nothing in common. So to make it true in all cases, we'll make a little addendum. And say we'll balance the equation out, since this is the side that we're going to end up with more, where we're counting things twice. We'll take away that where we count twice. So we'll say minus the cardinality of their intersection. And this is, again, always true for any sets A and B. And is referred to as the cardinal number formula. So you're going to have a few problems in 2.4, where essentially what's going to happen is you're going to be given this equation, and you're going to be given 3 of the 4 parts, and you solve for the remaining part that you don't know. It's a linear equation. All right, so you'll have a few problems like that. The bulk of our problems are going to be these, what we call survey problems, where we use a Venn diagram to sort out, given certain cardinalities, what number would belong to each region of the Venn diagram. So I'm going to go ahead and turn the page, give us lots of room to work here. And so we're going to work several examples of this, like you'll see when you work your homework. Now, first thing I'm going to do is I'm going to do a couple of these. Let's all right. So I'm going to have to write down all the information given first off. So remember, that means cardinality. So I'm going to say I've got a set A, and it has 57 elements. The intersection of a set A and B is 35. And the cardinality of the union of these two sets is given to be 81. And the cardinality of A intersect B intersect C, that is going to be 15. Cardinality of A intersects C is going to be 21. Cardinality of B intersects C is 25. Cardinality of C is 49. And cardinality of B complement is given to be, so that's everything not in B, is given to be 52. All right. So what we're going to do again is figure out in a Venn diagram what numbers belong to each region. Now, if you have a Venn diagram that is talking about 3 sets, then you construct it as such. 3 interlocking circles. So universal set, everything inside the box. Circle here. And then a third one right here. Now, anytime you construct a Venn diagram with 3 sets inside of it, so that universal set, there are 8 regions. If you just put 2 sets in there, there are 4 regions. If you have just 1 set, 1 circle in there, there are 2 regions. If it's just the universal set itself and no sets shown in there, there is 1 region, the universal set itself. That is its powers of 2. That is, if you then constructed a Venn diagram with 4 sets, it would have to have 16 regions, and 5 sets would be 32 regions. Next time we'll take a gander of what a 4 set 16 regions would look like, and it gets a little convoluted because you can't use 4 interlocking circles. But all the problems that you're going to look at will be no more than 3 sets. And so what I do is I know I've got sets A, B, and C. And I've got my 8 regions. And using this information right here, we're going to be able to go in and put what number belongs in each of those 8 regions. Now, notice there's also 8 pieces of information given. 1, 2, 3, 4, 5, 6, 7, 8. So you'll use each piece of information once. So when you're approaching this, your starting point is always the same. We're going to start right here. This region where all 3 overlap. That is what elements that would be common to all 3 sets. And that's right here. That would be A intersect B intersect C. Anything in here would have to be in all 3 sets. And we're given that number to be 15. So I write the number 15 there. And I'll just cross it out. I have used that piece of information. Any questions thus far? Okay. If not, now there's no hard fast rule where to go from here, but I will pick one of these guys. And this is where 2 of the 3 sets are overlapping. But this is where I start to separate out those cardinalities. So what I do is I just go through and basically from top down, and I figure out where I've got 2 of the sets overlapping. That number would be intersection. A intersect B is what I'm going to use. Now that would be here. All right, so I see it says 35. But what I write in this region right here is 20. Do you see why? The entire intersection of A and B, which is that what I call kind of the football shape, has to add up to be 35. So I would have to have 20 more in this region to get that total of 35. So it's really just the 35 minus the 15 I've already counted. And so I've got that. I've also got A intersect C. That would be these 2. And it says it is 21. So if that has to add up to be a total of 21, and I've already counted my 15, that tells me I have to have 6 in that region to get my total of 21. Use that. So then I've got B intersect C. And it says it's 25. So I'd have to have 10 to get my total 25. What's that? All right, so I already see right here, it says the cardinality of C is 49. Now that's all of C. And C has 4 regions total. And since I know 3 of the 4 It's really just a matter of adding 6 plus 15 plus 10, which is 31. I'll take that away from 49. And that tells me I have to have 18 here so that these four would add up to be 49. Got that. All right. Notice I've got 3 pieces of information left, and I have 3 regions which I have not accounted for yet. I'm going to go here, do exactly the same thing. It says A has to add up to be 57. So I've got 3 of the 4 regions accounted for. So I would have 20 plus 15 plus 6. That's 41. And so take that away from 57. I get 16. Would have to belong there. It's that one. Okay, so 2 regions left. I'm going to go ahead and tackle this one. Notice this says A union B. And that, remember, union means it has to be in one or the other, or it can be in both. So that's, and when we sketched the Venn diagram and shaded it, I shaded all of A, all of B. So it's every region making up A or B. And that's here, 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 here. So that's 6 regions, of which I have 5. And since A union B has to add up to be 81, I'll add up 16, 20, 6, 15, and 10. That's going to be a grand total of 67. So I'll take that away from 81. And I've got 14. All right. One last region, and that's outside of all 3 sets. And since B complement is everything outside of B, that would be 4 regions: here, 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 and then of course here, and of which I know 3 of the 4. So I can go 16 plus 6 plus 18. I get 40. And take that away from 52, and that leaves me with 12. And the problem is complete. Any questions on how I did this? Okay. Now, let's see if I can find it. My all-time favorite problem out of this book. All right, so we're going to do another type survey problem, except, example, it is not represented with just cardinalities of some generic sets. This is what I'll call a very much applied problem. All right. It's all in good fun. This one just makes me laugh. So I have nothing against country music. I love all genres. And I grew up with a mom who loved rock and roll and a dad who loved country music. So I remember watching Porter Wagner when I was a young kid. Most of you probably have no idea who I'm talking about. But anyway, that said, so I'm pulling this problem straight out of the textbook. So I'm going to read the problem first, and then we'll jot down the information. So here we go. Song themes. It was once said that country western songs emphasize 3 basic themes: love, prison, and trucks. A survey of the local country western radio station produced the following data. 12 songs station played 12 songs about a truck driver who's in love while in prison. 13 about a prisoner in love. 28 about a person in love. 18 about a truck driver in love. 3 of the songs were about a truck driver in prison who's not in love. 2 about people in prison who are not in love and do not drive trucks. 8 about people who are out of prison, are not in love, and do not drive trucks. And 16 about truck drivers who are not in prison. And then there's several questions with this problem. The very first one is how many songs were actually surveyed? And so the issue becomes if I would just add up those numbers directly, boom, just a 12 plus 13 plus 28 plus 18 plus 3 plus 2 plus 8 plus 16, I'm going to get way more songs than were actually played simply because of the overlap. So that is, they're getting counted in multiple categories, and that's where a Venn diagram comes in to play, where we can separate it out. So that's what we're going to use. We have basically a 3-set Venn diagram problem. All right. So fortunately, it was very difficult with our current format. I wish I could just share this up on the screen and have the whiteboard to go at the same time. But I'm just going to have to try to quickly write down that information so we've got it to work with. So we've got 12 songs. About trucks, truck drivers. Truck drivers who is in love. Wow. 13 about a prisoner in love. 28 about a person in love. 18 about a truck driver abbreviate there, truck driver in prison who is not in love. Three about a truck driver okay, my bad. Oh, that's the 3 about a truck driver in prison who's not in love. And then 18 about a truck driver in love. Right, now I got that straight. 2 about people in prison who are not in love. and do not drive trucks. Eight. Not prison. Not love. And do not drive trucks. And then 16, finally, about people, about truck drivers who are not in prison. Okay. Notice it is a piece of information just written in verbal form. So the first thing we're going to do is draw a Venn diagram. Three sets. So 3 interlocking circles. All right. So I'm going to label them L, people in love, people who drive trucks. And P, this set will be people who are in prison. 8 regions, we want a number in each region. So, and I always start right here where all 3 overlap. And let's see, very first entry, 12, there were 12 songs about truck drivers who are in love while in prison. That would be all 3. So I put my 12 right there. And check mark, I've used that piece of information. All right, so begin to spiral our way around. Let's say I look here. So I'm looking for information about songs that were prisoners in love. And I look right here, the very next one, 13 about a prisoner in love. Now, this is where things begin to separate out. Since that is the intersection of L and P, means I've already counted 12. So I need one more so that I have 13 in that set. Use that piece of information. Are we good there? All right. Now that would be 28, and it would be the entire set L. But notice right now I've got 2 unknowns. In order to use that, I would need to know 3 of the 4, so I can't use it yet. So I'll go to the next piece of information. Now, the next one was 3 songs about a truck driver in prison who is not in love. All right, so a truck driver who is in prison, who is not in love. Notice that is now this case, it's exactly describing that region. Truck driver, you got to be in the set T. In prison, so you got to be in the set P, but you're outside of the set L. So that's this region exactly. I don't have to do any subtraction. I know it's just saying that region is 3. Got it. Check. All right. Next one is about a truck driver in love. And again, truck driver in love. That would be the intersection of L and T. It says it's 18, of which I've counted 12. So there have to be 6. Now I could go back up and use this one. since 28 is the total of everything in L, and I know 3 of those 4 regions, I could add up 16 plus 12 plus 1, which is 19, and take that away from 28, and that's going to give me 9. So that if I added up all 4 of these, I would get my 28. So I've used that. All right. No, I now have 1, 2, 3 regions left, and I've got 3 pieces of information left to use. Now I got 2 songs about people in prison who are not in love and do not drive trucks. That is just this region right here. Exactly. The set P, but outside of the other 2 sets. So that's got to be 2. Got it. Now this next one is describing songs that would be outside of all 3. Songs about people not in prison who are not in love and do not drive trucks. And it says that is 8. All right, so that leaves me one last piece of information. I've got this one, songs about a truck driver who are not in prison. So that would be this region and this region. That would be the 2 regions of T outside of P. It says it's 16. I've counted 6, so I would need 10 more. And I've got all regions now filled in using that information. Any questions? All right, so, and just like the homework you'll have in 2.4, you'll construct a Venn diagram. You'll put in the numbers. What you'll actually have to do is do this work first, like we've done here on paper. Then on MyMathLab, it'll give you the Venn diagram with the 3 sets inside, and you'll have an empty box, a field that you'll fill the numbers all in. Once you've got that completed, then some of them may ask further questions using that Venn diagram. So like the first question here that this one asks here, how many songs were actually surveyed? And that now is just a matter of adding up all 8 regions. So I'll do that real quick. 8 plus 2 plus 3 plus 1 plus 12 plus 9 plus 6 plus 10, 51. So there were 51 songs surveyed. How many songs were just about truck drivers? Or about, I should rephrase that. If it had said just about truck drivers, then that's 10. If it just says how many songs were about truck drivers, then it's anywhere in the set T, and you would add up those 4 regions. That would be 15 plus 16, which would be 31. If it just says truck drivers. How many songs were about prisoners? And that would just be adding up everything inside the set P, which would be 15, 16, 18. How many were about truck drivers in prison? And that would be where the T and P overlap. So it would be 15. How many songs were about people not in prison? Now, don't forget these guys. They're any, because it's anything outside the set P, or initially, really what we're finding is the cardinality of P complement, everything outside of P. So it would be 8 plus 9 is 17, plus 6 is 23, plus 10 is 33. Okay. So, any questions on this problem? All right. If not, then I have one more problem I want to go over that you'll have a homework problem dealing with. There are times where I will get a type of problem that a Venn diagram is not applicable, because complements of one set are not the other sets that you have involved. That is, like, I have a problem involving 6 sets, but if I take the complement of one of them, I'm not getting another set within there. So again, Venn diagram not applicable. So an example might be this. If I were looking at, say, grade levels of basketball players, and had 3 levels that I was looking at, say junior high, high school, and college. And also in the mix, I'm looking at basketball positions, which would basically, the 3 basic positions are guard, forward, and center. The complement of a grade level is not a basketball position, and vice versa. In this case, what we use is what's called a contingency table. And so I'm going to draw out the contingency table we're going to use to find cardinalities of some sets based off this contingency table. So I'm going to label this set capital G, F for forward, and I'm going to use an N. This is for center. So those are basketball positions. I'm going to use a J for the junior high grade level, an S for senior high, and a C for college, which is why I didn't use a C for center here. All right, now I want to keep these numbers separated, so I'll put it. All right, so now I'm gonna put the numbers in here. 9, 6, 4, and this is total. Right, so and also down the row, across the row, we're gonna have totals. 9, 6, 4, 19, 12, 5, 9, 26, 5, 8, 2, 15. And then the totals down the columns, we'll have 26, 19, 15, and then 60. So note this column and this row add up. We have a total of 60 basketball players that we're looking at here. All right, so based on this contingency table, we are going to find some cardinalities of some various sets. And we'll kind of start easy. So here we go. I'm going to find the cardinality of J intersected G. So one thing in doing a problem like this, I want to be able to verbalize this. So I got J intersect G, but let's say it another way. We're talking about the set of basketball players that are in junior high and play the position of guard. So notice the key word for intersection again is and. They have to be in both. So from the contingency table, it's these 9. They are the 9 players that are both in junior high and play the position of guard. So cardinality, that set is 9. Any question on that? All right, do another. Cardinality of S intersected N. All right, so these would be the basketball players that are in senior high and play center. Notice it's also 9. It's these 9 though. Okay, so let's start ramping it up a little bit. Cardinality of N union with S intersected F. All right, so again, let's put it into words. They're going to be the number of players that play center. Remember, union translate as the word or. Center or are seniors and play forward. Okay. So if you are a center, there are how many? Total of what? 15 centers in this group. Or you are a senior and you play forward. So it's these 5. So collectively, it's those 5 from here. And these are disjoint sets, so I don't have to worry about overlap. Plus the number of, so that is, and let's put them in the kind of left to right order. The number of centers was 15, plus the cardinality of that set, which was 5. So it's a grand total of 20. Questions on that one? All right, do another. So let's find the number of folks who are S complement and are intersected with set G union N. All right. So we know, first off, we got this set. These are the people who are not seniors. That would be anyone in junior high and anyone in college. So here and here. Now, guard or what? Play. So we want the number of people who are not in senior high and play guard or center. So I'm going to put a little check mark since it has got to be the overlap of these guys and these guys. It's here, 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 and here. So that is 9 plus 4 plus 5 plus 2. And that adds up to be 20 as well. Questions on that one? All right. Let's do another one. Let's find the number of people who belong to the sets S intersected in complement union with C intersected with G complement. All right. So let's see here. It's going to be the number of people who are in senior high and do not play the position of center, or are in college and do not play guard. And so hopefully these two sets are disjoint, I can figure out how many belong here, how many belong here, and add those two together. So if you're a senior and do not play center, you're here and here. You're in senior high and you don't play center. So it's 17 people. That's here. If you're in college and do not play guard, you're here and here. So these are disjoint. And so I can just simply figure out that's 17, that's 10. There's nothing in common. So that is a total of 7. Questions on that? Contingency table. Okay. So just making sure there's no surprises in the homework. I've covered everything. Yeah. All right. So there are 14 total problems, 2.4. Putting a due date of this Thursday, next class, for that assignment. It is assigned. On Thursday, there is, I want to go over some material concepts dealing with infinite sets. And though there won't be any homework because my math lab doesn't have any homework for that, but it's important to cover. But there will be a quiz that I assign. On the following class, we'll put it all together, review, and I will be assigning the test over set theory, and we will be ready to move on to our next topic, which is, so that will be next week, starting next week, numeration and number theory. So